Computer Vision for Slamming and Navigation by Tanmay and Ashish. So in this video, we would be learning about what computer vision is, what is slamming and what is slamming and how it can be used for navigation. Plus, we'll also learn about some part of self-driving vehicles. So why do we need computer vision for self-driving vehicles? What's the use? And how does it help us? So isn't it obvious that in order to drive a car, the driver has to see the road, the people walking, the pedestrians. He needs to see its environment. Similarly, a self-driving vehicle should also have some set of eyes in order to see its environment, in order to navigate the road, make turns, maneuver itself when there's a lot of traffic or if there's a pedestrian inside or there's a pedestrian walking on the road. It needs to see, it needs to take an action on what it is seeing. Now, this can be achieved in a number of ways. So, what is computer vision exactly? What does it mean? What does it do? How it works? We learn about this. So, computer vision is a field of artificial intelligence and machine learning. So, in this, a program or a computer just takes a set of images, videos, runs some algorithms, some mathematical operations, and tries to take an action based on that information according to a set of instructions. So computer vision just works like a normal vision. It understands what it sees and it takes an action based upon what it sees, just like us. So how does computer vision work exactly? So a computer or a program takes input in the form of a video or an image from the cameras. Then computer runs some algorithms or mathematical models, functions, various operations on that image. Now for us that image or a video would mean something else, but for a computer it's just another set of matrices, multiple matrices in n-dimensional matrix. It could be a three-dimensional matrix to denote RGB colors. It could be an n-dimensional set of matrices denoting other forms of images. Now the computer needs to see this and take an action based on what it is, based on the set of instructions that it has already been provided. Now, how can this be achieved exactly? What do we really need to do in order to achieve computer vision, in order to achieve a good accuracy of computer vision, and how will this help us? So there are two main ways of achieving this a good accuracy of computer vision. One is by deep learning, other is by convolutional neural networks. So in deep learning, it basically mimics us. It mimics the learning process and then it remembers from what it learns. For example, you touch a hot pan and then you suddenly remove your hand from there. You learned that the pan is hot, so the next time you won't touch a hot pan. Similarly, in deep learning, it takes unprocessed data and it extracts some important features, some important points. For example, in the case of a pan, hot pan, the temperature was that feature. Where it was kept might also be a feature, such as if it was kept on a stove. Now, this unprocessed data goes through a set of mathematical functions, such as gradient descent, backpropagation. We'll learn about this later. And then it remembers those things, keeps them or stores them in a place, and then when the next time it encounters that situation, it runs through those algorithms and then it remembers what to do and what not to do. Now in the case of convolutional neural networks, it works and mimics our neurons, our brain. It processes the entire image and then gives us an output on what it is, maybe for classification, what it needs to do, maybe based on probabilistic methods. Now, there are different types of layers in the convolutional neural networks. One is called the convolutional layer, the other is pooling layer, and the last is a fully connected layer. We'll learn about this. We'll try to understand what it is later. So, what is simultaneous localization and mapping? Oof, that's such a long name. We'll just call us SLAM. It's easy, no? Slamming. So SLAM is like it creates a map of an environment. It might be an unknown environment, or it can be an known environment, but it would rather be an unknown one. And then it uses algorithms to track itself inside that environment. For example, if you're going through a jungle, now this algorithm will help you map the entire jungle. It will create a map of that jungle, and then it will try to track your location in that place. So computer vision slamming uses only computer vision to create the map and to track itself. It's like by seeing. You see all around you in a 360-degree motion and track yourself. When you move forward, you see the distance between things would change. Then it would try to process all of that information and then update your new position. So there are four sets of processes in slamming. So one is the position, which means that it would sense your position or try to sense the position of things in your surrounding by classifying them based on what it is. Then the next is sensing. It will sense the distance between objects, between you and the object. For example, distance between a tree or a building or anything. Then third is the map, which means it will create a map of whatever it is seeing based on whatever radius it can work upon. Then the last is the path, which means it will track a path for you and from where you have been to where you have gone. So it will try to map your routes that you have followed. So can slamming be done with something else? Like why just only cameras? Can we use something else or any other equipment or anything? Yes, of course it can be done. Like it can be done using radars. It can be done using sonars, lidars, and recently it can also be done using Wi-Fi, such as your automated robot cleaners, those robot vacuum bots, which clean your entire room, vacuum the entire room. It can also even work on Wi-Fi. It works on computer vision. It can work on radars. It can work on short sonars. It's and in the future it might even work on lidars and other sensors to create a better map of the surrounding. Now, in the case of a self-driving vehicle, now if we use computer vision, we can even use other sensors to provide a better accuracy in to predict what it needs to do next in order to move forward, to identify if there's another pedestrian, if there's another vehicle, if there's another animal, if there's a tree or anything, to take an action based on what it is seeing, what it is sensing around itself.
I would like to give you a basic introduction about SLAM algorithms. Firstly, what is SLAM? Simultaneous localization and mapping of the surroundings. So why do we need SLAM actually? SLAM is like the eyes of the EV. For an EV to see what is happening around itself, the only way to map and localize its surroundings is through SLAM. Very smart people came forward and designed various algorithms to perform SLAM. Some of the most efficient SLAM algorithms being EKF SLAM, fast SLAM, graph SLAM, etc. Some other algorithms which can perform SLAM are parallel tracking, LSD SLAM, etc. So in this presentation, we are going to discuss briefly about EKF SLAM. So what is EKF SLAM? EKF SLAM is extended Kalman filter SLAM. The term here to be noted is Kalman filter. So what is a Kalman filter? Kalman filtering is an algorithm which provides estimates of hidden variables based on inaccurate and uncertain measurements. So basically what a Kalman filter does is it observes the surroundings and the state of the system and tries to make predictions about the further state of the system. So why is it used? So Kalman filters are very good for systems which dynamically change. So the example for a dynamically changing system is an EV itself. The surroundings is not a constant system. So the Kalman filter is very useful for such purposes. So the extended Kalman filter is a slight modification of the Kalman filter algorithm. While the Kalman filter has linear functions in the mathematical representation, the EKF SLAM can have nonlinear terms in its mathematical representations. These EKF SLAM algorithms are very fast and they use less memory, which makes it ideal to be used in EVs. So coming to the EKF SLAM algorithm consists of three operations. Firstly, the motion model, the inverse observation model, and the direct observation model. The motion model is operated when the car reaches a new point of the scene. This model actually takes the state of the car. The inverse observation model operates when the car encounters new features in its surroundings. So this model actually captures the landmarks which are present around the car. So the direct observation model. The direct observation model uses both its state and the state of the landmarks to position itself correctly in the surroundings. So these all can be added to an estimator engine to build an automated solution to the SLAM. The similarities and differences between the extended Kalman filter and extended Kalman filter SLAM algorithm is the above. There are many differences and similarities between EKF and EKF SLAM algorithms, which can be viewed directly in this slide. So the operations of SLAM algorithm. The first operation is map initialization. Firstly, we consider the map has no landmarks. So the initial state of the car is considered as origin. Next, the car moves. So in a regular extended Kalman filter, the state of the car depends upon the old state of the car, the control input, and the disturbances of the system. So we represent this system using a mathematical equation involving matrices and functions. We can say that the state of the car R is a function of the state of the car R, the control vector U, and the disturbance vector N, where the R which is inside the function is the state of the car in the previous timestamp. So the state of the car is updated by this function. Next, the observation of mapped landmarks using sensors. So the EV contains onboard sensors which always take the input from the surroundings and convert them into electrical signals. So these measurements are captured by the extended Kalman filter, and these also are represented using the mathematical equations which involve matrices and functions as well. So here, why is the measurement taken by the sensors on board on the car? H is the observation function which forms the measurement Y. R is the state of the car. S is the sensor state. L is the landmark state, and V is the noise in the measurement. So this above mathematical equation forms the output and the measurement of the car. So this process occurs repetitively, iteratively. So we see the car moving along the road. This picture shows the brief working of an extended Kalman filter. So firstly, we know the prior knowledge of the state. So that is represented by x of k minus 1, comma k minus 1 and p of k minus 1, comma k minus 1. So based on this state, it predicts the present state of the system, which is the prediction step, which is p of k and k minus 1 and x of k, comma k minus 1. This is the present state of the system as predicted by the extended Kalman filter algorithm. So next, the update step. It takes the measurements from the surroundings using the sensors on board and it compares the prediction to the measurements. So this updates the state of the car to p of k, comma k and x bar of k, comma k. So this is the output estimate of the state. So the extended Kalman filter increases the timestamp to k plus 1 and the process repeats. In this way, the surroundings are localized and mapped by the sensors on board and the car motion is achieved. Thank you.